Hello, 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 everybody, and welcome back. We're looking at C3 now from our 2015 Canadian Open paper. So we've got three questions here. A, if n equals 3, determine all integer values of m such that m squared plus n squared plus 1 is divisible by m minus n plus 1 and m plus n plus 1. Okay. So we're given this nice n value, which kind of just simplifies things, makes you question why do we have the n. If you look ahead, you're going to see probably we're going to see these n's and these expressions again, but maybe in less constrained contexts. So right now, okay, n equals 3. So m squared plus n squared plus 1 is going to be m squared plus 10. M plus, whoops, it's plus n, right? Minus n was the first one, but then it's plus n plus 1. So that'll be m plus 4, and that'll be m minus 2. So if m squared plus n squared plus 1 is a multiple of both of them, is divisible by those, it's entirely possible that there's some overlap, but we could at least compare it to, like, for example, it's not, let me say quite clearly, it's not just as simple as saying, well, if m plus 4 divides m squared plus 10 and m minus 2 divides m squared plus 10, that happens exactly when m plus 4 times m minus 2 divides m squared plus 10. That's not the case because depending on certain values of m, there might be, say, a common factor of 5 or something. And m squared plus 10 might be something like 15, which has only one factor of 5, but you'd be assuming it has two factors of 5, that sort of a thing. So we have to be careful exactly how we word it, especially because it's a C-part question. Okay? So we can't say that, but we can say something to the effect, you can say something like m plus 4 and m minus 1 also divide m squared plus, well, not m squared plus 10, multiply them together. So m squared plus 2m minus 8. Okay, just multiply them together. Okay, and what we can do is compare these two, not dissimilar to how we did C part in the last question, which also had to deal with integers, if I recall correctly. And so what we can do is we can say, all right, I don't know what m plus 4 is or m minus 2 is. I know m is supposed to be an integer, so these will be integers. And so if m plus 4 divides m squared plus 10 and it divides m squared plus 2m minus 8, then it should divide their sum, their difference, those sorts of things. So m plus 4, m minus 2 must also divide we can go about this no matter, anyway. I'm going to try and get rid of the m squareds here. I think that might make things a little easier. M squared, so minus m squared plus 2m minus 8. And so that'll be negative 2m plus 18. Okay. Which I guess we could write as 2 minus 2m minus 9, I guess. Where to go from there? Well, we could look at just a single factor and say something like m plus 4 must divide negative 2m plus 18 plus 2 copies of m plus 4. Because if it divides this one and it divides this one, then it divides their sum. And that's really what we're basing this on. Now, why did I do 2 times m plus 4? Because now I want to get rid of this minus 2m. So this will be minus 2m plus 2m, and then 18 plus 2 times 4, which is 8. So m plus 4 needs to divide 26. So m plus 4 divides 26. Now we could do the same thing, but with m minus 2. So m minus 2 must divide negative 2m plus 18 plus 2m minus 2. And again, the m's will cancel out and be left with 18 minus 4, which will be 14. So m minus 2 must be a factor of 14. Now, did they say positive m's? Or nope, just integer values of m. So, what could we do? Well, we could say, what are the factors of 14? Because there's not going to be that many factors of 14. So, m minus 2 could be equal to minus 14, minus 7, minus 2, minus 1, 1, 2, 7, 14. So what would this make? M, minus 12, minus 5, 0, 1, 3, 4, 9, 16. And then what would be m plus 4? And if it's also a multiple, or a factor of 26, then we've got a good value for m. So add 4, we'll get negative 8, negative 1, 4, 5, 7, 8. We could have just added 6 from the first row if we'd wanted to. Or 20. So which of these are factors of 26? Well, negative 1 is. So that's a good one. 4 isn't, 5 isn't, 13 is. So m is negative 5 and negative, well, or negative 9. And there we go. So a little bit of work, but it's not really dissimilar to some things we've seen before, and slightly harder, but it's C3, so this is to be expected. All right, B part. Show that for any integer n, there is always at least one integer value of m for which m squared plus n squared plus 1 is divisible by both of them. Okay, so now we have a non-fixed value of n. What can we do? Well, we can do the same sort of thing that we did before, and so these are also factors, also divide. Their product, and their product will be m squared minus n squared plus 1, 2mn and a minus 2, or no, mn and a minus mn cancel out, n and a minus n cancel out, and then we'll be left with 2m's. Okay, so we need m minus n plus 1 to divide both of these. So we can do the same sort of thing, just compare and rearrange. And so what could we do? Well, we might want to get rid of the m's, I guess. Yeah. So we could say m squared plus n squared plus 1 minus m squared minus n squared plus 1 plus 2m. And that's going to be 2n squared minus 2m. Okay. Well, we could try and get rid of m, certainly. But I like this expression here. It's just got a single m. It's got an n squared in there, but we should expect our answer for the show there's at least one m based on n, where this works. We should expect our m to in some way be based on n. And so I wonder, could we just say if 2n squared minus 2m equals 0, this is true, and so n squared equal to m, just bring it over to the other side and divide by 2. So this should suffice. Okay, we could, I guess, double check this. Did this work in the last one? N was 3, and yeah. 3 squared made an appearance. That's kind of nice. I don't know whether or not I want to justify anything more. But, well, I guess we could say something like m squared plus n squared plus 1 would then be n to the 4 plus n squared plus 1. And does this indeed have a factor of n squared plus n plus 1? N squared, I'm just doing long polynomial division. N to the 4, n cubed, n squared. We'll be left with minus n cubed. And so minus n. We'll get n squared plus n plus 1, which gives me a plus 1. And that is also... So this here is m plus n plus 1, and this is m minus n plus 1. So it actually, we've set up a situation where both of these are equal. Which, of course, we did, because I said this was 0. Okay, yeah. But we have shown, double-checked that it does, in fact, work. And if you wanted to, you could probably consider all this your rough work and just say, well, you know, I did some rough work. You don't need to explain where it came from, but you could start at this line and say m equals n squared should suffice. And then you just show how this all works out. That would be a nice, short, sweet answer, but it doesn't hurt to show your workings. Alright, so there's always n squared. You can always let m be n squared. That's kind of nice. Alright, C part. Show that for any integer n, there are only a finite number of integer values m, for which m squared plus n squared plus 1 is divisible by both m minus n plus 1 and m plus n plus 1. Okay. So rather than just finding an answer, I think we're going to have to proceed much as we did in B part. And say something to the effect of, now how are we going to show there's only finitely many? Well, we're dealing with integers. And so if I could show something like m divides n cubed minus n, or so if I could show something like that, no matter what n is, this is an integer, it has only so many factors. So it'd be nice to look for something like that. Something involving m dividing something strictly in terms of n. Now, if you remember how C2 turned out, we didn't get quite so lucky with at the end of C2. We had something in terms of b divided something in terms of b, but you know, we'll see what we can get, but we've got a plan. So these guys divide m squared plus n squared plus 1, and they divide. Well, let's instead say it this way. We know for a fact these two will divide their product, which is m squared minus n squared plus 1 plus 2m. And so we're phrasing it carefully this time, these two divide m squared plus n squared plus 1 exactly if... So now I'd like to not have any m's lying around, just like we had in A part. We were slowly getting rid of m. So let's get rid of n squareds. M squareds, that's... So we could take one and subtract the other. Now this will still leave 2m kicking around, that's fine. So this is still the 2n squared minus 2m that we had, but now we could take each one of these one at a time. And so we could say m plus n plus 1 divides m squared plus n squared plus 1 exactly when it divides the sum here. So 2n squared minus 2m plus 2 times m plus n plus 1. Almost the exact same thing we did in a part. And so this will get rid of the two m's, the minus 2m's and the minus 2m's there, and we'll be left with 2n squared plus 2n plus 2. And so now we have something just in terms of n. Now, it's not just in terms of m over here, but we can work with this. We could say something like, for a given n, 2n squared plus 2n plus 2, it was plus 2n, right? Yeah. Plus 2n is fixed, and an integer. M plus n plus 1 is also an integer. And so a factor, 2n squared plus 2n plus 2. But this depends nothing on our choice, on the values of m. So this has a fixed number of factors. So m plus n plus 1 has a fixed number of possible values. Now, those, you could get some m's from there, but you'd also, if you just want just the list of m's, you'd have to do the same thing we did in part A, and so you'd also have to talk about m minus n plus 1. But we just want to show that the possible values for m are limited. So it has a fixed number of possible values. And so, since n is fixed, and m plus n plus 1 has a finite number. Did I say finite or fixed earlier? Let's change this to finite. Start using the language that they want in their response. Has a finite number of possibilities. How would we get m? We would just subtract n plus 1 from each of these. Has a finite number of possibilities. Then m has a finite number of possibilities. And that's what they wanted. For any n, there's only a finite number of values for m. We have shown it. So there we go. That's C3. Up next will be C4, and we are going to finish off our open paper. I will see you for that in the next video. Until then, take care.